Come on, my dears. Last time we had seen about diffraction of monochromatic light produced by a single slit, correct? Fraunhofer diffraction of a monochromatic light produced by a single slit. Fine. Now, in that we had obtained one formula regarding intensity of light at angle of diffraction, which is theta. Remember that formula? I theta equals to I0 sin square alpha upon alpha square, correct? What was alpha? Some sort of angle. And how was it related to angle of diffraction theta? Remember the formula? Alpha equals to pi d sin theta upon lambda, correct? Now let us do one thing. Let us change the width of the slit, and then what is the effect on width of central maximum? That is what we would like to study, okay? And for that, what we do? We plot a graph of intensity of light versus angle of diffraction for two different values of width of slit. First of all, we take d equals to 5 lambda, and then after we will take d equals to 2 lambda. Come on. When you take d equal to 5 lambda, just find out value of lambda upon d. Lambda upon d. It will be 1 upon 5. 1 upon 5, that is 0.2. And then in the second case, when you take d equals to 2 lambda, find out lambda upon d. It will be 1 by 2. 1 by 2, that is 0.5. Now tell me, here value of lambda upon d is 0.2. Here value of lambda upon d is 0.5. Compared to 0.2, 0.5 is bigger value. And you know, as lambda upon d increases, amount of diffraction increases. And as amount of diffraction would increase, the width of central maximum will also increase. You must have remembered what is called width of central maximum. Remembered? Here it is first order minimum. Here also it is first order minimum. And now distance between two first order minima is called width of central maximum. Here width is this much, and here width of central maximum is this much. Width of central maximum, correct? You can see in the diagram, compared to this width is bigger, because compared to this lambda upon d value here, which is 0.2, here value is bigger. As lambda upon d increases, amount of diffraction increases, and because of that, the width of central maximum also increases. Okay, fine. Let's go for next article. It is about what is called Fresnel distance. Fresnel distance, correct? S is silent, so don't pronounce it. You must pronounce this way, Fresnel. S is silent. Fresnel distance, shown by symbol ZF. Okay? My dears, in the textbook they have given very insufficient description, from which you will never understand one thing. Second thing, one diagram is required for understanding. The diagram also they have not given. Here I have drawn very clear cut diagram. So let us try to study, let us try to understand about Fresnel distance. First of all, you make parallel light rays having wavelength lambda perpendicularly incident on a slit of width small d. Okay, this much is the width of the slit. Fine. Suppose initially this screen is here, correct? This screen is here at distance capital D from the slit. And when the slit and screen, they are separated by distance capital D, at that time, suppose the graph of intensity of light versus angle of diffraction is this. When this is the graph, look here, this is the graph. What does it mean? That here there will be central maximum, here there will be first order minimum, here also first order minimum. Then you know distance between two first order minima on either side of central maximum. What is it called? Width of central maximum. So this much is the width. let it be small d double dash, small d double dash. So right now the width of center maximum is small d double dash, and last time we have studied about expression of width of central maximum. Remember that formula? It was 2 into lambda into capital D upon small d. 2 into lambda into capital D upon small d. Correct? Fine. So at present the width of central maximum is this much. Correct? D double dash. Fine. Now instead of light rays going straight, if they are made incident here, you can say this much is the angle which gives you amount of bending. Right now we take it as deviation delta. Deviation delta. Fine. Now when after passing through the slit, when light rays are made incident on the screen, this much width they cover on the screen. So this is also giving you width of the beam which is made incident on the screen. Width of the beam made incident on the screen. Okay? Right now it is this much. Fine. Now what does it indicate? Tell me. As this capital D will decrease, come on, D double dash also will decrease. As capital D decreases, D double dash also decreases. Fine. Now what I do, I just bring this screen closer to the slit. Okay. So I am going to decrease the separation between slit and screen. And suppose finally I keep it at distance d dash. And that distance d dash is such that it is half of some typical distance shown by symbol ZF called Fresnel distance. Okay. And if I am reducing the distance between slit and screen, and if I keep it at distance d dash, which is ZF upon 2, naturally when this distance will decrease, come on, d double dash also will decrease. And then when this d double dash, which is width of central maximum, decreases, finally suppose it becomes this much. Look here, this way. Correct? So now these two are the first order minima, and distance between them will give you new width of central maximum. Let it be d dash. Okay? So this d double dash will decrease to d dash, because this also decreases to d dash. Okay? This decreases to d dash, this also decreases to d dash. Fine. But tell me from the diagram that this new width of central maximum has just become equal to width of the slit, and width of the slit is how much? D. Correct? So this is new width of central maximum, which is from this formula, instead of d you just write d dash, and this is width of the slit. Okay? Fine. Now tell me, how much is capital D dash? We have taken is half of Fresnel distance. We have taken it half of Fresnel distance. So just put up this value of d dash in this formula. D dash is ZF upon 2. D dash is ZF upon 2. D dash is ZF upon 2. This 2 lambda as it is, small d also as it is. D dash is ZF upon 2. And small d also as it is. Now tell me, 2 will cancel. Find out ZF, d into d, d square. Lambda will come down. ZF equals to d square upon lambda. ZF equals to d square upon lambda. Now practically what do we find? If you keep distance between slit and screen very much smaller than this distance, which is called Fresnel distance, then it so happens that this deviation delta is negligibly small, and if deviation delta is negligibly small, then light rays would pass almost without getting bent, and at that time, because light rays propagate on a rectilinear paths, we can apply ray optics. So tell me, what is this ZF? ZF or d square upon lambda? It is such a distance. If you keep distance between slit and screen very much smaller than Fresnel distance, then the ray optics can be applied, because the deviation delta is negligibly small, light rays are passing on the straight path, and hence you can apply ray optics. Correct? So how would you define Fresnel distance? Distance between slit and screen which is negligible as compared to some typical distance for which ray optics can be applied is called, that typical distance is called Fresnel distance. By formula, it is ZF equals to d square upon lambda, correct? When distance between slit and screen is kept very much smaller than some typical distance such that ray optics can be applied, then the typical distance is called Fresnel distance, shown by symbol ZF. Formula is d square upon lambda, where d is width of the slit and lambda is the wavelength of monochromatic light used in the experiment. Okay, fine. Now let us see diffraction pattern in telescope and microscope. You know, we use optical instruments to see the things very clearly and if possible up to the largest size of the image, correct? Fine. Those instruments are, you know, you have studied in third semester about telescope and about microscope, correct? Fine. Now tell me, in both of them, in telescope also and in microscope also, what happens? That there is an objective lens, and the light rays coming from some object, they are made incident first on the objective lens of telescope or microscope. What that lens will do? It will allow only limited part of the wavefront to pass through it. And you know, physical effect arising due to limited part of a wavefront is nothing but diffraction. So light waves which enter in the objective lens of telescope or microscope definitely undergo some diffraction. And because of diffraction, ultimately the image is obtained which is not very clear. The edges are not very sharp, and that sort of image itself is known as diffraction pattern. Okay, fine. You know how is that diffraction pattern? Diffraction pattern is something like this. Exactly at the center, we find some bright spot like a circular disc. This bright circular spot obtained at the center is known as Airy's disc. Airy's disc, which indicates central maximum. Just surrounding to that, we have first order minimum, then first order maximum, then second order minimum, then second order maximum, then third order minimum, then third order maximum, and so on. Altogether, this pattern is called diffraction pattern. Whichever is a central bright circular disc, that is called Airy's disc, and the surrounding different order maxima rings are called Airy's rings. Airy's rings. In textbook they have not drawn any diagram, so you may not understand. I hope you must have understood from here. Okay, fine. For examination purpose, no need to draw this diagram. It will not be asked because it is not there in the textbook. Okay. Now let us see some very good points of difference between interference and diffraction. First point regarding definition. What is called an interference? Come on. Physical effect arising due to superposition of two or more than two waves is called an interference. I repeat, physical effect arising due to superposition of two or more than two waves is called an interference. What about definition of diffraction? Physical effect arising due to limited part of a wavefront is called diffraction. Correct? That is the first point of difference regarding their definition, regarding their meanings. Fine. Second point we take, come on, fringe width. In case of stationary interference pattern obtained in Young's double slit experiment, you must have noticed in the graph, the peaks were having same height, and at the peak we get intensity of light equal to I0. So maximum intensity obtained in bright fringes are same in case of stationary interference pattern obtained in Young's double slit experiment. So here fringe width is same, and here what about fringe width? You know, here in case of diffraction, look, This is the fringe width, correct, for central maximum. This is the fringe width for first order maximum. This much is fringe width of second order maximum, and so on. Here we find that the widths of different maxima are not same. Widths of other order maxima other than central maximum are same, but width of central maximum is double than that equal width. Width of central maximum is double than the equal width of other order maxima. Okay, and in case of stationary interference pattern, the widths of all the fringes are same, correct? So here width is same and here widths are not same. What about intensity? Maximum intensity in all the bright fringes in case of stationary interference pattern are same. And here for diffraction, come on, this is central maximum, this is first order maximum, this is second order maximum, and then as order of maximum increases, intensity goes on decreasing. As order of maximum increases, come on, intensity of light goes on decreasing. Okay, fine. And what about pattern? Interference pattern can be obtained without diffraction. Interference pattern can be obtained without diffraction, but diffraction pattern cannot be obtained without interference. Diffraction pattern cannot be obtained without interference. Okay, let me repeat all the 4 points of difference. What is called an interference? Physical effect arising due to superposition of two or more than two waves is called an interference. Physical effect arising due to limited part of a wavefront is called diffraction. What about fringe width? Here all the fringes have same width in case of stationary interference pattern obtained by Mr. Young in his double slit experiment. Here widths of all the fringes are not same. Width of central maximum is double than equal width of other order maxima. What about intensity? Here maximum intensity in all the bright fringes are same. Here as order of maximum increases, intensity of light goes on decreasing. And for pattern, for interference pattern, diffraction is not required. But for diffraction pattern to take place, interference is a must. Without interference, you cannot have diffraction pattern. Okay, fine. Now kindly read this statement of illustration number 5. Come on, read it. Look, last time we had talked about angular width of central maximum. What was that angular width? 2 theta 1. Formula for that was 2 into lambda upon small d. Fine. This is in case of first light. But in case of second light, naturally, when you change the light, wavelength will change. Instead of lambda, I am putting lambda dash. Instead of 2 theta 1, I am putting 2 theta 1 dash. Fine. Now, this is new angular width, which is 70% of initial angular width. Why 70%? In the statement they have said that when we use second light, it so happens that there is a decrement of 30% in the width of angular width of central maximum. If angular width of central maximum decreases by 30%, then what is left in balance? 70%. So new angular width of central maximum is 70% of initial angular width. Initial angular width is 2 theta 1. Its 70% means multiply by 70 divided by 100. this part as it is. Okay, fine. Now this 2 theta 1 value is how much? It is 2 lambda upon d. Come on, 2 lambda upon d into 70 upon 100 as it is. This right hand side also as it is. Now simplify. D will cancel. 2 will cancel. Correct? Lambda dash will be equal to lambda into 7 upon 10. 7 upon 10, that is 0.7. What is value of wavelength of first light? They have given in the statement 6000 angstrom multiplied by 0.7 gives you answer 4200 this many angstrom. What is the right way to put the symbol of angstrom? This is the right way. This dot, this empty circle, you must put exactly at the top in the center, not sidewise. This empty circle you must put exactly over this pointed end. Okay, not sidewise. Please take care. Now in the second half of the statement, you know what have they said? This whole experimental setup is now immersed in some unknown liquid, correct? And when we do that, it so happens that in that unknown liquid, there is also decrement in the angular width of central maximum by same percentage, that is by 30% only. If angular width decreases by 30%, then what is left? 70%. What is left? 70%. Okay. Now find out wavelength of light in that unknown liquid. Look, what was the formula of here for wavelength? Lambda dash we got lambda into 0.7, correct? And here instead of lambda dash, I am putting lambda double dash. You know what is lambda double dash? It is wavelength of light in that unknown liquid. And here also why it is lambda into 0.7? Because here also angular width decreases by 30%. If angular width decreases by 30%, then what is left? 70%. And 70% of this, finally we got lambda into 0.7. Lambda into 0.7. So I am writing lambda into 0.7. Now lambda is wavelength of first light and it was given to you 6000 angstrom multiplied by 0.7. So the answer is, come on, 4200 angstrom, correct? In the examination, they may change that percentage. Suppose they may say that when the whole experimental setup is immersed in some another unknown liquid and suppose angular width decreases by 20%, suppose. If angular width decreases by 20%, what is left out? 80%. So at that time you will write here 0.8, correct? Lambda into 0.8, got it? Accordingly you can find out the wavelength of light in that unknown liquid. Okay. Now kindly read this statement of illustration number 6. Come on, have you read it? Come on, what is the formula of intensity of light at angle of diffraction theta of monochromatic light produced by a single slit? In case of Fraunhofer diffraction of a monochromatic light produced by a single slit, this is the formula: I theta equals to I0 into sine square alpha upon alpha square. Now they have talked about maxima, different order maxima in the statement. And at each maximum, the intensity of light in that particular region is maximum. Suppose you are talking about this region, correct? Then maximum intensity is this much. You are talking about first order maximum, maximum intensity is this much. You are talking about second order maximum, maximum intensity is this much. Okay? So wherever it is the maximum, might be central, might be first, might be second, dash, dash, dash. At each such point where maximum takes place, the intensity has got maximum value. And don't you know, whenever any function is either becoming maximum or becoming minimum, in both the times, come on, its first derivative is 0. So at each of the maxima, if intensity of light is maximum, then first derivative of this intensity must be 0. Here variable is alpha, So I should take first derivative of I with respect to alpha, that is di upon d alpha, di upon d alpha, and that should be 0. First derivative of any function is 0, meaning thereby that function might be maximum or minimum. Given to us is maximum value. For any functional value becoming maximum at a particular value of variable, remember its first derivative becomes 0. So here di upon d alpha is 0, that is d by d alpha of I, d by d alpha of I. What is I formula? I0 sine square alpha upon alpha square, I0 sine square alpha upon alpha square, and that should be equal to 0. Because I0 is constant, can be taken out. So I0 is taken out, left is d by d alpha of sine square alpha upon alpha square, d by d alpha of sine square alpha upon alpha square, that is equal to 0. Now this I0 as it is, take this as u, take this as v, so you will find it something like d by d alpha of u upon v, u upon v. There is a special rule for taking derivative of a ratio. What is that rule? You should write denominator as it is multiplied by derivative of numerator minus numerator as it is multiplied by derivative of denominator divided by square of denominator, divided by square of denominator. Come on, this I0 as it is. Now we have to write derivative, we have to write denominator as it is, denominator as it is. What is the denominator right now? Alpha square. So I am writing alpha square as it is, and then multiplied by derivative of numerator. What is derivative of numerator? D by d alpha of sine square alpha, it is 2 sine alpha. Then further you take d by d alpha of sine alpha, which is cos alpha. Further you take d by d alpha of alpha, which is 1. Correct? Derivative of sine square alpha is 2 sine alpha. Derivative of sine alpha is cos alpha. Derivative of alpha with respect to alpha is 1. After putting minus sign, come on, numerator as it is multiplied by derivative of denominator, d by d alpha of alpha square, it is 2 alpha, and divided by square of denominator, square of alpha square would be alpha raised to 4, and that should be equal to 0. Now transfer this I0 in the denominator here, 0 upon anything would be 0. Transfer this in the numerator, alpha raised to 4 into 0 will be 0. In short, this part would be 0. This part is 0. Now transfer this part over here, from minus it will become plus. Just come on, cancel whatever you can. 2 alpha square sine alpha into cos alpha equals to 2 alpha sine square alpha. Tell me what you can cancel. 2 ones are 2, correct? Alpha ones are alpha, sine alpha ones are sine alpha, fine. Now take this cos alpha in the denominator here. So sine alpha upon cos alpha, sine alpha upon cos alpha, and that equals to alpha. But what is sine alpha upon cos alpha? It is nothing but tan alpha. So what is the required condition? Tan alpha equals to alpha. For whichever point on the screen, if this condition is getting satisfied, then at that point we will have formation of particular order maximum. Correct? So this gives you condition of maxima, but in terms of alpha. Correct? Fine. Come on, my dears, let us proceed further in the theoretical part. Listen, now 2 articles we will study. In the chapter you will never understand that much, and they have not given clear cut diagrams, and here very nice diagrams are drawn with all the necessary labels. You will definitely understand from here. Okay, please kindly pay your very nice attention on the board. Fine. What is called angular limit of resolution and angular resolution power of a given telescope? First of all, we will go for angular limit of resolution. It is some sort of minimum angle which we will show by symbol alpha minimum. Okay, fine. Now tell me, for what purpose do you use this astronomical telescope? For obtaining the images of very distantly lying stars. Correct? Stars are very far away from from us, and they seem to us like point like. So consider two point-like stars which are lying close to each other. These are two point-like stars. We find them point-like. For stars, I have used the symbols S1 and S2. What we do? We try to catch their images in the same view of the telescope. At a time, we like to see the images of both the stars. Fine. So when we focus that telescope, what happens? We get images of these two point-like objects on the focal plane. Fine. So this is the focal plane on which you will get the images of these two stars. Image of S1 is obtained here, which I have shown by symbol I1. Image of S2 I have shown here with symbol I2. Even color also I have not changed. For blue colored object, I have shown image with the blue color. For pink colored object, I have shown image also with the pink color. Correct? Fine. At present, these light rays which are emanating from these two stars subtend angle, say alpha, with the objective of a telescope. Fine. Now, when this alpha value is greater than certain limit, we find that these two images can be seen very clearly and distinctly. That is, far away from each other, separately we can see them. Actually, this is the image, but actually image means what here? Diffraction pattern. Diffraction pattern. Then you may have question that how diffraction effects are introduced. Very simple. These point-like objects, if they are stars, they would emit light rays. So when light rays are propagating, you can consider the propagation of spherical wavefronts from a point-like source. Correct? So here spherical wavefronts are propagating this way, and ultimately they are incident on this objective of a telescope, and the entire wavefront cannot pass through. Only limited part of that wavefront will be passing through the objective. Only limited part is passing, so you know diffraction effects will occur. Because what was the definition of diffraction? Remembered? Physical effect arising due to limited part of a wavefront is called diffraction. So here light rays will undergo some diffraction, and because of diffraction effects we will have image clarity rather spoiled. Okay, in the image we don't find the image so clear. Each image is nothing but a diffraction pattern like this, in which the central maximum is obtained in the form of bright circular spot, which we call Aries disk, and surrounded by different minor maxima, that is different secondary maxima, first order maximum, second order maximum, third order maximum, and so on. These all circular rings are called Aries rings. Correct? So here image means diffraction pattern, and just for the sake of convenience I have not shown Aries rings. I have shown only the central part, that is Aries disk. But these two images at present are obtained quite separate from each other. Fine. Now by side I have also drawn the graph of intensity of light versus angle of diffraction. That intensity distribution is shown by such a graph. Fine. Tell me, for this graph, this is first order minimum on upper side, this is first order minimum on lower side. So this much distance would be distance between two first order minima, and that much distance would give you width of central maximum. Width of central maximum. Correct? Fine. Now these two central maximum points are away from each other. Images are said to be separated. Okay. Now let us do one thing. Let us bring these 2 point-like objects closer. Suppose we shift those 2 point-like objects closer to each other this way. When you bring them closer, naturally these two images also will be moving closer. At one stage, the situation is like this. Like this means what? Just look in the figure very minutely. This angle is found to be smaller than this. Suppose that angle we show by symbol alpha minimum. Correct? What is that angle? I will tell you. Whatever is this angle, same is this angle, vertically opposite. And these two central maxima, they were moving closer to each other, and ultimately in this situation they have been arranged this way. This way means what? Look here. This is the central maximum in the diffraction pattern of first object. This is the central maximum in the diffraction pattern of second object. Here you can see this is the first order minimum in the diffraction pattern of first object. See, when the central maximum is over, the surrounding black ring indicates first order minimum. So here there is a first order minimum in the diffraction pattern of first object. Similarly, here there is a first order minimum in the diffraction pattern of second object. So tell me, what is superposing on what at this point? Here there is a superposition of central maximum of diffraction pattern of first object with the first order minimum of diffraction pattern of second object. Here central maximum of diffraction pattern of second object superposes on the first order minimum of diffraction pattern of first object. By side, if you see, I have shown the intensity distribution curves, and this is the graph of intensity versus angle of diffraction for second object. This is the graph of intensity of light versus diffraction angle for first object. Now tell me, at this point, what superposes on what? This point I have shown with the yellow color. At this yellow colored point, central maximum in the diffraction pattern of first object superposes on the first order minimum in the diffraction pattern of second object. Here, the central maximum in the diffraction pattern of second object superposes on the first order minimum in the diffraction pattern of first object. Fine. When this sort of situation occurs, these two images are said to be just separated. Okay, fine. Why we say just separated? Because now if these 2 point-like objects are brought slightly closer, correct? Even slightly also, if you bring them closer, then these two images will get mixed with one another. At this very situation, they are about to get mixed, but yet they have not been mixed up. So we say these two images are just separated from each other. Fine. Here these two images are definitely separated, far separated, and here they are just separated, correct? But yet these two images are said to be of two different objects. We can have clear distinction between them. Then how long the distinction between the images can be made? How long, correct? That certificate is given by Mr. Lord Rayleigh. We call it Lord Rayleigh's criterion. What is Lord Rayleigh's criterion? To see the images separated from each other. What is Lord Rayleigh's criterion? Very simple. In the diffraction patterns obtained of two point-like closely lying objects obtained by some given optical instrument, if central maximum of diffraction pattern of first object is superposing on the first order minimum in the diffraction pattern of second object, or it is obtained away from it, then those two images are said to be of two different objects. This very fact gives you Lord Rayleigh's criterion. In the diffraction patterns obtained of two point-like closely lying objects obtained by given optical instrument, if central maximum of either diffraction pattern either superposes on the first order minimum of second diffraction pattern, or it is obtained away from it, then those two images are said to be separated. I repeat for the last time. When we obtain images of two closely lying point-like objects using a given optical instrument, if central maximum of first object is obtained either on the first order minimum of second object, or it is obtained away from it, then those two images are said to be separated from each other, or those two images are said to be of two different objects clearly. Correct? This statement gives you Lord Rayleigh's criterion. I repeat, when we obtain images of two closely lying point-like objects using given optical instrument, if central maximum of diffraction pattern of one object is obtained either on the first order minimum of diffraction pattern of second object, or it is obtained away from it, then those two images are said to be separated. This very statement gives us Lord Rayleigh's criterion. Okay. Now tell me, if you bring these two objects even closer than this distance, then this angle will be smaller than this alpha minimum, and when alpha is less than alpha minimum, at that time these two diffraction patterns will just overlap each other. That time we cannot say that images are obtained separately. No, we cannot say that. Correct? Once this situation is arisen, at that time these two images are about to get mixed. Now further, if you reduce this angle, then they will be definitely getting mixed. Correct? As long as alpha is equal to alpha minimum or alpha is greater than alpha minimum, at that time we say images are separated from each other. Okay, fine. Such an angle, alpha minimum, is called angular limit of resolution for a given telescope. Come on. How would you define angular limit of resolution of a given telescope? When images of two closely lying point-like objects are obtained just separate using a given optical instrument, the angle subtended by light rays coming from those two objects at the objective of that instrument is called angular limit of resolution of that optical instrument, which we have taken at present as telescope. I repeat, when images of two closely lying point-like objects obtained by given telescope are just separate, then angle made by light rays coming from those two objects at the objective of a telescope is called angular limit of resolution of that telescope, shown by symbol alpha minimum, and its reciprocal is called resolution power of that telescope. See now, very clear cut definition of angular limit of resolution of a given telescope. How is the definition? Look here. When images of two closely lying stars are obtained just separate using a given telescope, comma, the angle subtended by light rays coming from those two stars made at objective of the telescope is called angular limit of resolution for that telescope, shown by symbol alpha minimum. I repeat, when images of two closely lying stars are obtained using a given telescope, just separate, comma, the angle made by light rays coming from those two stars at the objective of the telescope is called angular limit of resolution of that telescope, shown by symbol alpha minimum, and its reciprocal is called angular resolution power of that telescope. Fine. Now, alpha minimum formula, the derivation is not in our syllabus. You have to simply remember that formula. Formula is very simple. Alpha minimum is equal to 1.22 lambda upon capital D. But remember, this formula is to be used only in radian, because this 1.22 is in radian. Okay, fine. And when this has the unit radian, naturally angular resolution power will have unit 1 upon radian, that is radian inverse. Radian inverse. Now tell me in the figure, what is this distance x? X is distance between two central maxima. But when images are just separated, correct? Fine. So let us find out this distance x now. See, when you are talking about stars, stars are those objects which are lying very far. And using telescope, when you obtain images of very far objects, naturally those images will be obtained on the focal plane. So this must be focal plane, and distance of focal plane from the optical center of a lens is nothing but focal length. So this much distance is focal length, this much angle is same as this because these two are vertically opposite. So this also will be alpha minimum. And what is this? Arc. What is the formula of arc? Radius into angle. Radius into angle. Radius is f, angle is alpha minimum. So distance between two central maxima, let it be x, and from the figure x is radius into angle. Radius is f, angle is alpha minimum. F as it is, alpha minimum formula is this, 1.22 lambda upon capital D. Mind well, what is this? This is distance between two central maxima. Distance between two central maxima is x, which is this much, correct? Now in textbook they have written this as width of central maximum. Width of central maximum. It is very wrong. Width of central maximum is not this much. Width of central maximum is double than this. Look, this is central maximum of diffraction pattern of first object, and its width means distance from here to here, and distance from here to here it would be x plus x. X plus x, that is 2x. From here to here you can see these two are first order minima, and distance between two first order minima is called width of central maximum. It is this much, and the same distance is not x but it is 2x. So width of central maximum is 2x, means 2 into x means 2 into this, 2 into this. So width of central maximum will be double than this. Okay, fine. And now, what is the angular limit of resolution for Hubble Space Telescope? NASA, you must have heard the name of that institute, NASA, NASA, National Aeronautics and Space Administration. National Aeronautics and Space Administration, very famous institute from USA. They have launched one telescope in the space called Hubble Space Telescope, and for that Hubble Space Telescope the value of angular limit of resolution is the minimum in the whole world. It has angular limit of resolution minimum, it is 0.1 second. Mind well, this is the symbol for second, which is the angle which is 60th part of 1 minute angle. And you know what is 1 minute angle? Again it is 60th part of 1 degree angle. and this is not 1 second, this is 0.1 second. Okay, 1 second is 3600th part of 1 degree, but this is not 1, this is 0.1 second. So you can say this angle is, as compared to degree, it is 36,000th part of 1 degree. 36,000 part of 1 degree, that much small is the angular limit of resolution for Hubble Space Telescope. Okay, for human eye, this angular limit of resolution is found to be from 1 minute to 2 minutes. From 1 minute to 2 minutes, correct? If you take minimum in here, suppose 1 minute, then what does it mean? For human eye, if angular limit of resolution is 1 minute, what does it mean? If you try to see two point-like objects which are far from you, and if the light rays coming from those 2 point-like objects make angle at the human eye lesser than 1 minute, then that person cannot see those two objects clearly. He cannot see them separately. The images will get mixed with one another because angle is lesser than alpha minimum. As long as alpha is equal to alpha minimum or alpha greater than alpha minimum, then those two images can be seen separately. Okay, fine. Now we go for linear limit of resolution and linear power of resolution for a given microscope. We use microscope for viewing the objects which are very close to us but which are very small. With the naked eye we cannot see them clearly. For having magnified and clear view, we just use microscope. Okay, fine. Here is a objective of a given microscope, and this is the principal axis. Fine. In case of microscope, you must have remembered that we place point-like objects very close to principal focus. So I have shown here point-like object. Now distance of focal point from the optical center is equal to focal length. From here to here, this distance would give you diameter of objective. Capital D. Fine. If this much is capital D, what is half of that? Half of that will be D by 2. Correct? Fine. Now suppose a light ray emanating from this point-like objects which is made incident at the top of the objective. Suppose it makes angle beta with this principal axis. Now in this right angle triangle, find out tan beta. Tan beta means opposite to beta divided by adjacent to beta. Opposite to beta, it is D by 2, correct? Divided by adjacent to beta, which is this much side, and this much means how much? Actually it is focal length f. But for this object, its distance from this optical center is object distance shown by symbol u. Right now u and f, they are nearly equal. U is nearly equal to f. So instead of f, I am putting instead of u, I am putting f here. This much is object distance, this much is focal length. They are nearly equal. So instead of u, I am putting now f. Bring these two down. So d upon 2 into f. D upon 2 into f. Now find out d upon f. Find out d upon f. Transfer this 2 over here. So d upon f will be 2 into tan beta. D upon f will be 2 into tan beta. Correct? Now tell me. If you place one object, then naturally you will have one image. And then in that diffraction pattern, this is Airy's disk and this is Airy's ring. You can have more than one ring also. Here I have shown only one ring. This is Airy's disk and this is Airy's ring. Fine. You know this one is nothing but central maximum, correct? And this much will give you width of central maximum. Width of central maximum. And that width of central maximum, let us find out. The way you had taken this angle as angular limit of resolution of a telescope shown by symbol alpha minimum, similarly here we take this angle as theta minimum, which is called angular limit of resolution for microscope. Fine. Now this is theta minimum, correct? This much is arc, and this image is obtained at this much distance from the optical center of a lens, which is called image distance, correct? Fine. Now what is the formula for arc? Radius into angle. Radius is this much, which is V, angle is theta minimum. Radius into angle. Angle is theta minimum, and its formula is also same as alpha minimum. So formula is 1.22 lambda upon capital D, 1.22 lambda upon capital D. But mind well, this diameter is diameter of objective of microscope, and this diameter is diameter of objective of telescope. Mind well, this is radius, this is angle. Angle is theta minimum. Its formula is same as this, 1.22 lambda upon capital D. In textbook, by mistake they have written here F. It's very wrong. In the description given below the figure, they have correctly given this value, this into F. But right now, that this into V they have given, but in the figure they have committed a mistake. In the figure they have written this bracket into F, which is wrong. It is not F, it is small v, correct? In the description they have put this value correctly, fine. So now this much is the width of central maximum, this into V, got it? Fine. Now tell me, these two point-like objects, when they are brought closer to each other, correct? Then at one stage we obtain this sort of situation. This sort of situation means what? Images are just separated from each other, just separated from each other. At that time, whatever is the linear distance between these two point-like sources, that linear distance is called linear limit of resolution of a given microscope, shown by symbol dm. How would you define it? Very simple. When images of two point-like objects are obtained just separate using a given microscope, then whatever is the distance between those two point-like objects is called linear limit of resolution of that microscope, and its reciprocal is called linear resolution power of that microscope. I repeat, when images of two point-like objects obtained using given microscope are just separated, the distance between those two objects is said to be linear limit of resolution of that microscope, and its reciprocal is called linear resolution power of that microscope. In short, linear limit of resolution is some sort of linear distance, and hence it has unit meter, whereas linear resolution power is reciprocal of that linear limit of resolution, so it has unit 1 upon meter, that is meter inverse. Got it? Fine. Now tell me, there is a formula for finding linear limit of resolution of a given microscope. Just remember that formula, derivation is not there in your syllabus. Its formula is 1.22 into lambda upon capital D into small v upon small m. What is small m? Magnification. And for a lens, what is the magnification formula? You have studied in third semester. M equals to v by u. M equals to v by u. V as it is. Instead of u, I am putting f. Instead of u, because u and f are nearly equal, instead of u I am putting f. Instead of u I am putting f. And now find out v upon m. Find out v upon m, it will be f. Come on, v upon m is nothing but f. So 1.22 lambda upon capital D into f. Fine. Now take this f down in the denominator's denominator. So 1.22 lambda upon d upon f. Come on, d upon f. Find out d upon f from here. D upon f value is ready with us. How much it is? 2 tan beta. So this d upon f can be replaced by 2 tan beta. But actually speaking, this angle beta shown in the diagram is found to be very small, and for very small angle beta, tan beta is nearly equal to sin beta. Tan beta is nearly equal to sin beta. Fine. So instead of tan beta, I can write sin beta. Write it here. Tan beta is nearly equal to sin beta. Now tell me, how the quality of a microscope is decided? That microscope is said to be of best quality whose linear limit of resolution is minimum. So just to reduce this linear limit of resolution, what we do in practice, we keep this objective immersed in oil which is filled in some cylindrical tube, and that sort of objective which is immersed in oil which is kept in some cylindrical tube is called oil immersion objective. Oil immersion objective. It is called oil immersion objective. Then you may have a question, why should we do that? For what purpose? I am showing you. If wavelength of light wave in air or vacuum is lambda, then wavelength of same light wave in a denser transparent medium having absolute refractive index n is found to be nth part of lambda. Nth part of lambda, that is lambda upon n. Lambda upon n. So instead of lambda, now we should write lambda upon n. Instead of lambda, write lambda upon n, where n is absolute refractive index of given transparent medium. Here that given transparent medium in case of oil immersion objective is oil, and for oil absolute refractive index is greater than 1. So when value of n is more than 1, naturally denominator will be more and hence ratio will be less. So linear limit of resolution will be less, and if linear limit of resolution is less, then linear resolution power would be more. So after using oil immersion objective, what you can do? You can increase this denominator, you can decrease this linear limit of resolution, and after decreasing this, you can increase linear resolution power. Got it? Here in the denominator, n into sin beta, this part is having no unit, no dimension. This part, n into sin beta, is unitless, dimensionless. Unitless, dimensionless. Such a part is called numerical aperture. What is it called? Numerical aperture of a given microscope. And for given oil immersion objective, when you increase the value of n, and then n into sin beta will increase, numerical aperture is increased, dm is decreased, and once dm is decreased, then linear resolution power can be increased. For both telescope and microscope, remember, whenever you are asked to purchase say telescope or microscope from market, you should purchase that telescope and that microscope whose limit of resolution is minimum. Might be angular, might be linear, but limit of resolution should be minimized so that power of resolution can be maximized. Okay, thank you.